Hey everybody, this is Larry. This is day 25 of the January Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. I'm sitting very awkwardly today. I don't know if people can tell at home or whatever, or if you're watching. Usually I'm a little bit closer, but I'm doing the thing where I have my feet elevated because it is still very much in pain. I don't know what happened, honestly, because I got it. I mean, if you watch yesterday's video, I told a story about how I got injured. You should watch it. I think it's kind of funny, but I don't know. I'm not gonna tell it again. But anyway, I got injured on Tuesday. Wednesday, I felt like I was fine and I was running okay. Like I ran 4 or 5 miles or something on Wednesday, and then only yesterday it started being in pain. I don't know if I like did something in my sleep or something, but right now my foot is very swollen as I'm looking at it. At least like the part, it's like bruised and swollen, and I haven't been able to walk that much in the last 2 3 days. Today, for example, I only let's see, what did I do? I only walked 3 miles, which is actually like very light for me. And every step in pain might remind you. So I don't know. Anyway, so I'm sitting very awkwardly. So let me know if I hope the mic is close enough because it's not as close as it usually is. But well, let me know in the comments if the audio is a little bit off for sure. All right, let's take a look at today's problem. We have 2948. Make lexicographically smallest array by swapping elements. Okay, so we have zero indexed array of positive integer nums and a positive integer limit. All right. In one operation, you take any two indexes and swap them as long as the delta is less than or equal to limit. Return the lexicographically smallest array that can be obtained by performing the operation any number of times. Okay, and then it's just a definition of lexicographically. Okay, well, first of all, I think like I bring this up a lot because it comes up a lot, which is what lexicographically smallest mean, right? Lexicographically smallest just means that usually there's a greedy way of doing this, right? I mean, not sorry. Let me phrase that a little bit better way. What I mean is that when you have to select between two answers that satisfy a condition, you have to choose the greedy one. And greedy, I don't mean in the same way that it is like a greedy algorithm, but just like a greedy choice, if you will. And what I mean by that is that if you have two numbers, right, and this happens in some base k numbers for any definition of k, right, where and for that we can just say a regular base 10 number, right, because it's easier to say. It makes sense once you say it that way, right? Because then now you have like say 800 or right, 1000, right, some big number, and then the second number could be 1 5, but then I don't know, 1 here, and it doesn't matter if the rest of the numbers are big, right? It doesn't matter if the rest of the numbers are big because the most significant digit in which they differ, this is bigger, and it could be all zeros for all you know, right? And that's basically what lexicographically smallest. I mean, in this case, I was saying which one is bigger, but same thing, right? If this is a zero, like if the first digit is a zero, it doesn't matter if they're all nines. This number will still smaller than this number, right? And then you can think about that in other contexts, right? In this one, I guess I don't know. They're just random numbers, so there's no base per se, but you can think about that in the same way. But like a similar problem that people often see is like what I call base 26, which is from A to Z, right? Like alphabets is A to Z. There's 26 distinct letters, characters, and so you can think of it as a 26 number, and right. So these are just things to think about. Anyway, okay. Okay, so that's the first thing, right? The second thing is that, and for us, it means practically. Actually, let me add one more thing. So that's basically a thing that we know about lexicographically smallest. And so, what does that mean, right? That means that whatever you do, like in this particular one, I didn't even really see the limits yet, or like we didn't think about the limits yet. But what it means is that if you're able to get the first digit to be, for this problem, as small as possible, it doesn't matter what the rest is, right? So that's basically the thing, right? Sometimes for similar problems, you may have a cause that you have to be under or whatever, but as long as you can be, and this is where the greedy part comes in, is that as long as you could get the first digit to be as small as possible, it doesn't matter what the rest of the digits is, right? Unless it ties, then you care about the second digit, etc. But that's what these are the things that we think about when you think about lexicographically smallest, right? Okay. Okay, let's see. I and J. So I and J doesn't really matter in the sense that there's no function on I and J. It's just that for any two numbers in which the difference, the delta, is less than or equal to the limit, and then we can swap them. Well, what does that mean, right? Well, swapping is an operation that is transitive because you can do any amount of them and there's no cost or anything like that, right? Any number of times. So, and what I mean by that is that if you can swap, if f of AB, in this case, what do I mean by transitive? It means that, right? It means it implies that f of A and C is equal to true. In this case, f is swappable, right? And in this case, it is true. And you can, I mean, this is like, I don't know if there's a strict proof, but you can just do like a 3 example thing, right? Like you can, if you can swap A and B, and then that means that you turn A and B to B and A, and B and C, well, that's trivial as well, right? Then now you can say A and C, or maybe A, B, C, right? Then now you can swap it to from A to B, so B, A, C, and then swap B to C, right? So C, A, B, and then swap it again, so C, B, A, which is dot. And therefore, you swap from A to C and C to A, right? So that's basically a very basic proof of transitive property, because now that you prove it for A, B, and C, you can prove it for every, or like it's true for everything else, right? Okay. So these are the mathematical background. I think sometimes people have to let me know in the comments what you think about how I've been doing so far on the explanation. I know that I've been kind of focused on the math a little bit, and I think I do get comments about that. I sometimes explain. I mean, to me, honestly, this is actually more basic than I would like to explain. Or not even that I would like to explain, but like these things I go very fast on, but this time I'm trying to slow it down. But sometimes people still say that this is too mathematical. I don't know where the right balance is necessarily for every video. So, we're all learning here on this earth. So let me know in the comments, if this is too deep, not deep enough, do I need to go back to first principles, and so forth. One thing I would remind you though is that these videos, or in general, are meant to be a companion video, meaning that you worked on this, you tried this problem, and and you maybe get stuck somewhere, right? It's not meant to be like, oh, let me read this problem with you. I mean, I guess I did read the problem with you, but it's not meant to be like every, like, I don't know. So, and sometimes it hits, sometimes it misses anyway. But that's not the intention in any case, right? Like, otherwise, I don't need to make the same video more than once. It's just different, and I try not to, but, I just do the daily ones because, I don't know. Because to me, I don't remember this, even though I probably have done this problem, but I don't know. I mean, just by mathematical probability, I probably have done this problem, but I don't remember it, right? Anyway, okay, so that's a little bit of a side rant, or just a survey, if you will. But yeah, so anyway, so now we know that f, right, and that means that this is transitive, right? And what does that mean? Well, that means that now, if you think about it now in graph terms, right? If A is connected to B and B is connected to C, but then now that you could do that with any element, then you kind of keep on going with every single element, right? And then if you kind of visually build that out, you're like, okay, well, like in a graph theory kind of way, if you build that graph, if you draw it out, chart it out, whatever, then now you go, okay, well, if A is connected to B and B is connected to C, and it goes on, right? Like C is connected to D, then you could go from A to D or D to A. And then now we tie it all back together. And all back together meaning that, okay, well, now we're trying to find the lexicographically smallest array, right? So what does that mean? Well, if A is connected to B and B is connected to C is connected to D, and A is the first or the earliest element on the index, then of those 4 numbers, we would just greedily, there's always a way to swap because of the proofs, then we want to take the smallest number in the front. And then and then second smallest number in the second place, because in an inductive way, right? Because now we prove optimal in the first element because it's the smallest element. Then now we do it for second and dot dot dot. And that's pretty much it. So for every component, we maybe I gave away that a little bit, but for every index, we look at everything that it can be connected to, and then just get the smallest number at any given time. You can do this in any number of ways in terms of implementation, because you can think about what I just said, and what I said, maybe be like, okay, well, we're repeatedly getting the smallest number, so maybe that's a heap problem, and that's fine, right? Like that's a reasonable thing to do. Maybe another way would be like, okay, well, we repeatedly get the smallest, but it is in order, and we don't. After you sort it, you don't need to reuse any number or something like that, right? Well, in that case, then you could just sort, right? So that's another implementation. So and honestly, both of them are fine, right? Like heap, sure, there's a higher constant, but it is still going to be n log n for the most part in the upper bound. Like, yeah, maybe for some certain properties, maybe it'll be a log k or something instead, but for this problem, it'll be log n, so it'll be probably fine. At least off my head, maybe I'm wrong, but that's fine. Log n or log k is still going to be fast enough for this problem, which is why I didn't think about it, right? That's all I need to do. Okay, right? So then now, okay, and then now just think about implementation details, right? So then now we said that if A is connected to B, is connected to C, and then dot dot dot, and now you have this kind of chain of stuff, right? Well, what does this chain of stuff mean? It means that you can do connected components, and there are a couple of ways you could do connected components, right? And pretty straightforward. A very common one is disjoint set union, right? DSU, which is fine, also, honestly. And maybe you could even write things. Yeah, you can write things with like BFS or something like that. I don't know. I mean. And I think the only thing about that is that you have to be careful, right? Because nums is 10 to the 5th. It means that if you're not careful, your graph could be n squared, right? And what I mean by that is just by edges, right? And one very trivial example, I don't know if the numbers don't have to be unique, right? It doesn't seem like it. There's 2 ones here. But if you are like very, not careful, or just didn't think ahead, I mean, and some of this just comes from experience, because trust me, everything I warn you about, I have done the wrong thing before. I'm like, oh, okay, well, Larry, you've been, now you're learning, right? But yeah, but for example, if you have all ones, well, and you just kind of manually connect the graph with a for loop, either implicitly or explicitly, you may go, okay, well, let's connect this one with this one, this one with this one, and dot dot dot, and then it just becomes n squared, right? So you have to avoid that, but that's also fine-ish, right? So yeah. I mean, it's fine-ish as long as you don't make it n square. So you have to not look at every edge. And yeah, like I said, you could do connected components, you could do BFS, you could do depth of search, you can do a lot of things with respect to like recursion, or use a stack to kind of calculate all these things. It's fine. Like, and in fact, if you solve this problem before, try solving it in a different way than you usually have it, right? Yeah. Okay. So how would I think about this one? Well, actually, I think I'm going to try something really funky. Maybe I will try something really funky, just to be different, honestly. And the key part is just noting that these numbers, all you care about is, well, let's say you can't do this by itself, but let's say you sort the input. Then what happens? Well, that means that your connected graph is just, it will always be adjacent elements, right? Because A connected to B and B connected to C implies A is to C, as we said, transitive property. Because of the transitive property, we don't need all the edges. So we don't have to explicitly say, okay, A is connected to C. We just have to say, okay, A is connected to B, is connected to C, like almost like a chain linked list or something like that, right? So yeah, so if we are able to sort it that way, then that will be good enough, right? And yeah, what else is there to say? Yeah, and as a result, then now when you look at and kind of you visualize this, and maybe I should draw this out because I'm visualizing in my head. But also honestly, one comment that I have for y'all at home is that these videos are not meant to be passive, right? And what I mean by that is that in general, and I don't know how people learn. Maybe some people learn better the other way. I don't know. But the thing is that you're not learning to understand. I mean, sure, that's part of it, but you're learning to learn, right? Like you're learning to execute, not just writing it. You're not learning the solution. Anyone can learn the solution. You're learning to understand the solution, right? So, and what I mean by that is that, or what's practical about that is just, look, hopefully you can afford, paper and stuff and just draw it out with me, right? As I'm talking about it. I am going a little bit fast, but you do have the technology of slowing it down, watching it and slow it down, maybe, I don't know, and rewatching it. But anyway, but after you sort it, my visualization is just that after you sort it, and every element and the edges will be next to adjacent elements, right? And when that happens, well, you can think about what's the inverse of that. That means that the graph will be disconnected, also on adjacent elements, right? And as a result, then now, what is one chunk of connected component means, right? Well, then now you can compress that by just taking the smallest number and the largest number, right? So that could be an interval thing, right? And that's really, I don't know if this is the cleanest way to write it, because I think honestly the least riskier thing is probably using like a breadth first search or connected components. So definitely, if you want to implement now, you want to pause and you haven't gotten it yet, definitely pause and then just implement it that way. I think that's probably the way that I would do it during a contest, is using a disjoint set union. I don't have to think about it too much with respect to that, right? Because then now you sort, you keep the index and so forth. But I am going to play around today. I don't know if maybe it's the dumb foot pain wanting me to kind of do something adventurous. But yeah, that's what I would do. Right, so let's get started then. Right, so we have enumerate nums, we have index x, right, in this. So we want to sort by x index, right? And the reason is this, so that as we said, what is it called? Maybe naming things is hard. That's whatever. That naming things is harder than all the things I just said, maybe. But yeah, and then now you sort, right? And now that gives us all the numbers, as we said, and then the index will be well, just the index from the original thing. And yeah, I guess you can do the thing with segment, but you don't even need the thing anymore, right? Because then now you can think about this as just chunks at a time, right? Yeah, okay. I mean, there are, like I said, there are a lot of ways you can write this, right? So yeah, so then now maybe you have maybe I feel like there's a cleaner way for me to write this, but I always don't, so I don't know, right? So you have a chunk, right? Your previous is equal to I don't know, negative infinity or something weird. It's some sentinel value, and you'll see why I do that in a second. Also, this is intentional. I know that there's a math.infinity. I don't know. I'm not going to explain it today, but people always leave comments. I don't know. I've been doing this for 20 years, and people, I don't know. But I do make mistakes sometimes, so don't take me as, infallible. Anyway, okay. Yeah. So then now for x index in pairs, we want to say, okay, well, if the difference between x and in the previous number, if this difference is greater than limit, or not equal to, I suppose, actually greater than limit, then now we want a new chunk, right? So then we want to process chunk, and then just chunk is equal to new chunk, and then chunk append x index, maybe, right? And then at the end, we also want to process chunk. Though you can also maybe, yeah, you could do it this way, or you could also use a sentinel to make sure that it always kicks off, meaning like pairs.append, like, I don't know, infinity or something like that, and then, I don't know. But it's fine either way, I don't know, it doesn't matter, right? And okay, because a chunk, right? So what does a chunk contain? I don't know, right? So a chunk contains what's it called? X pairs and index pairs, right? Not X, but like order X's inside the chunk, and then order indexes, right, inside the chunk, right? Meaning that everything inside this chunk you can swap, right? I mean, that's all we're talking to, right, about, right? Order X's, well, order X's will be in order. So then now we're just talking about chunks, right? The indexes, right? So maybe in a lazy way, I mean, you could do this actually in a smarter way, but maybe we can even do it here, but I don't know, it's fine, right? For X, it doesn't even matter. Index in chunk, index C is dot append chunk, and I know that you could write this in one liner, but I'd like to be explicit for videos. But yeah, so now you have the index C's, and then and the thing is that, well, as we said so many times about greedy, we want to be greedy here, right? So we just sort to the left, and then now we mash them up one by one, and that's all, right? So for I don't know, I in range of length of chunk, we have chunk of 0, chunk of I 0. This part's a little bit ugly, maybe I could, okay, fine. But I want to write something like I, X, and enumerate chunk, and this is actually X and then the O index, which we sort and we don't care about anymore. You can, I don't know, maybe this interface is a little bit awkward. Maybe we can write this here instead then, right? So here chunk, or maybe we can call it like, I don't know, this is a little bit premature optimization maybe, but nonetheless, maybe it's just, so you have something like this, right? And then you have process, oops, X's and indexes, and then after that, after you process it, we set it to empty, and this is equal to empty, and then xs.append x, index c's.append index, right? But then now you have to kind of do this thing, which is a little bit awkward. Anyway, so then now you have x's and indexes. Maybe then now we don't have to talk about the chunk anymore. Okay, so then we don't have to do this, but we do want to sort. And then now we can do for xi in enumerate chunk. We want to say, well, the index c sub I, which is going to be the smallest index inside this chunk, right? And this is actually so then now we just want to replace that, and that's it, right? So nums of this index is equal to x, and that's it. Now that we, I mean, I don't know, maybe I guess we should set up an answer, fine, right? So answer is equal to none times n, right? Where n is the length of nums, and then here we just have answer, and we just update it. I mean, maybe you could pass it up or whatever you like, but that's it, right? And that's it. And then at the end we just return answer. And hopefully that should be good. I mean, mistakes do happen all the time. Huh. How did this happen? Well, 135 is definitely wrong. Did I forget to sort something else? Index C sort. Index D should be sorted. Oh, I'm dumb. We should always append. That's why. How did that even? How is it not missing numbers? Actually, that is wild. Did I forget to sort? Huh? I don't know. No, it's still wrong. So yeah, something else is wrong because that doesn't make sense actually by itself. But oh, I didn't update previous. That's why. New x is equal to previous is equal to x, and there you go. Okay. Yeah. Looks okay, right? Silly mistakes as always. Oh, Larry. But yeah, let's give a quick submit, and hopefully I didn't do anything silly. And yeah, there you go, 1761 day streak. Bit of a fast complexity, that's okay. I mean, usually I'm slower. But yeah, so what's the complexity here, right? I mean, we just sort a bunch of times. This is sorting. I guess that's actually just, it's more than twice because technically this is inside a loop. But we just sort, and that's it, right? And yeah. I don't know if you could hear people being loud next door, but that's okay. But yeah, this is n log n, right? So this is n log n just for obvious reasons. We sort the entire thing. But you may be like, oh, there's a lot of sorting here. Well, I mean, the way that I think about this is that the worst case is n log n right here inside this for loop. I don't know how people do it normally, but you can kind of just play around the numbers, right? The way that I do it, for example, if there's n chunks, meaning that you have n chunks of one element each, what is the worst case? Well, this is just going to be sorting one element, and you have n of them, so it's just going to be O of n, right? If you have one chunk of n elements, this is n log n. And then just, I don't know, and so as a result, it's an n log n worst case, because the summation of that is going to be in between, just because of the intermediate value theorem kind of thing, right? Like it goes from O of n to n log n, and then it's going to be something in between, right? That's just how the summations work. That's how I think about it anyway. Maybe there's a harder proof than that, but yeah, but that's what up about, right? If you really want to try, you could. I mean, but that's mostly because sorting is log n, right? There's no quadratic e things here, so it doesn't go crazy. Meaning that like you can also play around with like, okay, well, what if we have two chunks? Or I guess the hard chunk would be like, what if you have square root of n chunks of square root of n elements each, right? Well, then you have square root of n log square root of square root of n log square root of n, right? And of course you can take out the square root out of the log, but then it's just 1/2 times square root of n log n, and then you have n of those, right? Or you have square root of those, so you sum that up, and that's going to be log n log n, right? I don't know if that was too fast, but you can write it out. I trust you. You're smart. You can write things. But yeah, so it's going to be n log n. I don't know why I want to prove it today, because I feel like sometimes people ask me about amortization and stuff like that. But yeah, that is all I have for today. Let me know what you think. Thanks for watching. Hopefully this video is long enough for me to get the ice out of my fridge to ice my leg, my foot. Because I want to do a 6-mile run tomorrow, but it's so swollen. And at the way, I don't know, maybe it's not that swollen anymore, but it definitely is way pink and like red and all these things. I don't know. And the most important part is that it still hurts a lot. So anyway, it is what it is. That's all I have. Thanks for watching. Stay good, stay healthy, to good mental health. Have a great weekend, everybody. I'll see y'all later and take care. Bye bye.